Hi there, everyone. Welcome back to my channel. Today, we're diving deep into one of the cornerstones of linear algebra, the Rank-Nullity Theorem. Let's make a start. Let's start with the basics. The Rank-Nullity Theorem is all about understanding the balance between the dimension of the domain vector space, the rank, and the nullity of a linear transformation, where, apart from the dimension of V, rank of T is dimension of range of T, and the nullity of T is given by dimension of the kernel of T. Learning about the dimension of a vector space, rank, and nullity of a linear transformation is crucial for understanding and proving the Rank-Nullity Theorem because these concepts form the foundation of the theorem itself. Studying range and kernel are vital for calculating the rank and nullity respectively, as well as for understanding dependencies in the domain. Let me recall about these terms. The dimension of a vector space is defined as the number of basis vectors in that space. In simpler terms, it is the minimum number of vectors required to span the entire vector space, where a basis is a set of linearly independent vectors in the vector space that spans the entire space. For a set of vectors to span a vector space, it means that any vector in the space can be written as a linear combination of the vectors in that set. Simply, the set generates the entire vector space through scaling and adding its vectors together. Linearly independent vectors are a set of vectors where none can be expressed as a linear combination of the others. In other words, the only solution to the equation c1x1 plus c2x2 up to cn(xn) equal to 0 is when all the scalar coefficients are equal to 0. If we talk about the nullity of a linear transformation, it's simply the dimension of the kernel of that transformation. The kernel or the null space of a linear transformation T is defined as the set of all vectors in V such that their image under T is 0. On the other hand, the rank of a linear transformation is the dimension of its range space. And the range space is the set of all possible outputs, or images, the transformation can produce. Here's the theorem in formal terms. For a linear transformation from V to W, where V is a finite dimensional vector space, it holds that the dimension of V is equal to the sum of rank and nullity of T. Now, why is this theorem so important? It's not just an abstract mathematical concept. It provides a framework to understand how linear transformations work and gives insights into the structure of matrices. Essentially, it reveals how many degrees of freedom a transformation has and how much information is lost when applying the transformation. To prove this theorem, we'll break it down step by step. Let the nullity of T, that is, the dimension of the null space of T, be K. Then, by the definition of the dimension of vector space we discussed earlier, the basis of the null space of T is the set of elements U1, U2, continuing until UK. Now, here's the key idea. If you're working with a basis for a subspace of dimension K, you'll observe that each vector is unique, indispensable. But it is also observed that the full space has dimension greater than K. If we talk about proper subspaces, you need additional vectors so that each added vector must carry something new to the table, something no combination of the others can replicate. So, by extending the basis with the help of a finite number of vectors, you can form another basis for the full vector space. So, the total extended basis for V consists of all the basis vectors of the null space of T, as well as a finite number of distinct vectors in V, say V1, V2, continuing up to Vn. Now our aim is to prove that the set of the images of V1, V2, continuing up to Vn under the map T is actually a basis of the range space of T. To do this, firstly we've to show that this set spans Rt. That is, any element of Rt can be written as a linear combination of the vectors tv1, tv2, continuing up to tvn. So, let's consider an arbitrary vector w in Rt. By the definition of range space, this means that we'll find at least one element from the domain space V such that the image of V under T is W itself. Since we've already considered B as the basis of V, the vector V can be written as the linear combination of all the vectors in B as follows. Here, alpha is and beta is are scalars in the field under which the vector space has been defined. So, we get V is equal to sigma running from I equals 1 to k of alpha I ui plus sigma running from I equals 1 to n of beta ivi. Now we'll operate on v under t, which is also equal to w. By the definition of linear transformation, t preserves the operations and we get sigma running from I equals 1 to k of alpha itui plus sigma running from I equals 1 to n of beta itvi. Here, in the first term we see that all UAS are the basis vectors of the kernel of t, which implies all the TUAS will become 0, and thus we get W as a linear combination of the vectors tv1, tv2, up to tvn. Hence, the vectors tv1, tv2, up to tvn span the range space of T. Next, let's see how the set tv1, tv2, up to tvn is linearly independent in order to cement our claim with an absolute proof. To validate this part, let's assume that the linear combination of its vectors equals 0. We intend to solve for the coefficients alpha is and show that all the values obtained are equal to 0. The transformation T distributes and scales consistently, so as a result, we have T of sigma running from I equals 1 to n of alpha ivi equals 0. Here, we observe that the term sigma running from I equals 1 to n of alpha ivi is itself a vector in V such that T maps it to 0. From this, it follows that it resides in the null space of T. This suggests that this vector can be uniquely written as the linear combination of the basis vectors of Nt. Thus, we have sigma running from I equals 1 to n of alpha ivi equals sigma running from j equals 1 to n of beta j uj, where beta js are scalars for j being from 1 to k. On sending the term on the right-hand side having the vectors uj's to the left-hand side, we observe that we get a linear combination of the basis vectors of v equal to 0. Then, by the definition of basis, the values of alpha is and beta js are all 0. So, it confirms that the images of v1, v2, vn are linearly independent vectors. Finally, let's put it all together. The rank of T, or the dimension of the range of T, is the total number of its basis vectors, which is n, and can also be written as n plus k minus k. If we consider the bases of the null space of T and the vector space V, the dimensions of Nt and V are k and n plus k respectively. Consequently, it transforms into dimension of V minus dimension of Nt. So, rank of T is equal to dimension of V minus nullity of T. In conclusion, it finally leads to dimension of V is equal to rank of T plus nullity of T. And with that, we've proven it clear, logical, and precise. This might sound theoretical, but the Rank-Nullity Theorem generates a spectrum of consequential findings. The Rank-Nullity Theorem isn't just theoretical, it's a tool used in solving systems of linear equations, understanding the properties of vector spaces, and even an invertibility of matrices. If you found this explanation helpful, make sure to like, subscribe, and share this video. And don't forget to leave your thoughts or questions in the comments. I'd love to hear from you. Until next time, stay healthy, everybody.